There is a side of the moon that no human being has ever seen with their own eyes. Not an astronaut, not a telescope operator, not a single person standing on the surface of this Earth has ever looked up and caught even a glimpse of it. And for 50 years, NASA sent mission after mission to the moon and deliberately chose to ignore it. Every single lander, every single rover, every single crewed spacecraft, they all went to the same side, the near side, the side facing us. And the other half of the moon, a surface area roughly the size of Africa, just sat there, waiting, unexplored, avoided. Now, when you first hear that, it sounds like a conspiracy. It sounds like there's something out there that someone doesn't want us to find. And honestly, the truth is almost more unsettling than any conspiracy theory could ever be. Because the reason NASA avoided the far side of the moon for half a century isn't because it's boring. It's because it is genuinely one of the strangest places in the entire solar system, and we are only now, right now, in the last few years, beginning to understand what's actually out there. If this is the kind of thing that makes your brain light up, stick around, because this one goes deep. And if you haven't subscribed yet, now is a really good time to do that, because we cover stuff like this constantly, and you do not want to miss what's coming next. So let's start at the beginning. The moon is tidally locked to the Earth. That means it rotates on its own axis at exactly the same rate that it orbits around our planet. One rotation equals one full trip around the Earth. The result of that is that the same face of the moon is always pointing toward us. Always. It never changes. The moon is essentially showing us one side for eternity, like a performer who only works the front of the stage. This isn't unique to the moon, by the way. Tidal locking happens all over the solar system. Many of Jupiter's moons are tidally locked to Jupiter. Many of Saturn's moons are the same way. It's actually a pretty common outcome of gravitational physics over long periods of time. But what is not common is what happened to the moon as a result of this arrangement. Because spending billions of years with one face pointed toward Earth and the other face pointed toward deep space created two completely different worlds on the same object. And this is where it starts to get genuinely weird. If you look at the near side of the moon through a telescope, the side we can always see, you'll notice these large dark patches spread across the surface. Ancient astronomers called them maria, which is the Latin word for seas. They thought they were actual bodies of water. They're not. They're vast plains of solidified lava, enormous flat regions where, billions of years ago, the moon's interior was so hot that molten rock poured out through cracks in the crust and spread out across the surface, eventually cooling and hardening into what we see today. These dark plains cover about 31% of the near-side surface. They give the moon that distinctive face-like appearance that humans have been staring at and projecting patterns onto for as long as we've existed. Now look at the far side. The far side has almost none of that. The dark plains, the maria, they cover only about 2% of the far side surface, 2% versus 31%. The same moon, the same object, two completely different geological histories written on opposite sides of the same rock. That is not a small difference. That is an enormous, glaring, scientifically puzzling difference that we have been struggling to explain for decades. The far side is almost entirely ancient, heavily cratered highland terrain. It's rough and battered, and looks almost nothing like the side you've been looking at your whole life. And for a long time we had no idea this was the case because no one had ever seen it. The first human civilization to get a look at the far side of the moon was the Soviet Union, and it happened in 1959. A spacecraft called Luna 3 swung around the moon, took a series of photographs of the far side, and transmitted them back to Earth. The images were blurry and low resolution by any modern standard, but they were real. They showed what was actually there. And scientists immediately noticed that the far side looked completely different from the near side they'd been studying for centuries. It was rugged, cratered, ancient-looking in a way that the near side simply wasn't. And that observation raised a question that nobody had a good answer to. Why would the two sides of the same moon look so different? That question sat largely unanswered for decades. We had theories, but no real evidence to support any of them, and the reason we couldn't get the evidence is exactly why NASA avoided sending missions there for 50 years. Communication. Here's the fundamental problem. The far side of the moon, by definition, never faces Earth, which means that if you put a spacecraft on the far side, it is permanently out of line of sight with our planet. There is a 2,000-mile thick ball of rock sitting directly between your spacecraft and every antenna, every radio dish, every control center back home. You cannot talk to it. You cannot receive its signals. You cannot send it commands. It is, from a communications standpoint, completely cut off. In the early days of lunar exploration, during the Apollo era, this wasn't just an inconvenience. It was an absolute mission-ending constraint. When the Apollo astronauts went around the far side of the moon during their orbital passes, they experienced what mission controllers called loss of signal. For about 45 minutes during each orbit, the crew was completely unreachable. No communication at all. And that was considered one of the most tense and nerve-wracking parts of every mission, even though they weren't landing there, even though they were just passing through. The idea of putting astronauts or equipment down on the surface of the far side, where they'd be permanently cut off, was simply not viable with the technology that existed at the time. So everything went to the near side. Every Apollo landing, every robotic lander, every rover. The near side of the moon became incredibly well studied, and the far side remained a mystery wrapped in radio silence. But here's what makes this story so interesting. The far side wasn't just harder to reach. It turned out to be different in ways that made it simultaneously more scientifically valuable and more technologically challenging to explore. Every discovery about the far side made scientists more desperate to get there and more aware of how complicated it was going to be. Let's talk about one of those discoveries, because there is a feature on the far side of the moon that, when scientists first measured it properly, made some of them genuinely question their understanding of how worlds are formed. It's called the South Pole Aitken Basin, and it is, without any exaggeration, one of the most remarkable geological features in the entire solar system. The South Pole Aitken Basin is an impact crater, but those words do not do it justice. When we say crater, most people picture something like the craters you can see on the moon's near side. Bowl-shaped depressions, maybe a few kilometers across, maybe 100 kilometers for the big ones. The Tycho crater on the near side is about 85 kilometers in diameter and is considered one of the largest and most impressive features on the side of the moon we can see. It's enormous by human standards. It's a genuinely massive hole in the ground. The South Pole Aitken Basin is 2,500 kilometers across. To put that in perspective, that's roughly the distance from New York City to Las Vegas. If you place this crater on the continental United States, it would cover roughly half the country. It's not just wide, it's also extraordinarily deep. The basin floor sits about 8 kilometers below the surrounding terrain in some places. And the rim, the mountains and ridges that form the edge of this ancient impact scar rises up to as high as 8 kilometers above the floor in certain sections. That's almost the height of Mount Everest, and it forms a ring around a depression the size of a continent. This is the largest confirmed impact crater in the solar system, and it's sitting right there on the far side of the moon, largely hidden from our view, a monument to some absolutely catastrophic collision that happened in the early days of the solar system, probably 4 billion years ago or more. Now, the thing about a crater this size is that it doesn't just make a big hole. An impact that powerful goes deep. It punches through the outer layers of whatever it hits and excavates material from far below the surface, which means the floor of the South Pole Aitken Basin is not made of the same stuff as the moon's outer crust. It contains material from much deeper inside the moon, material that would otherwise be completely inaccessible to us without drilling hundreds of kilometers into the lunar interior. Scientists believe that if you could properly analyze the rocks on the floor of this basin, you could learn things about the moon's internal composition that no other location on the moon could teach you. You could potentially figure out how the moon formed, how its interior differentiated over time, whether it has a proper metallic core, and how the early solar system behaved in those chaotic first hundreds of millions of years when everything was smashing into everything else. That's extraordinary. That's the kind of scientific opportunity that comes along maybe once in a generation, and for 50 years we couldn't reach it because there was no way to talk to anything we put down there. But the scientific mystery of the far side goes even deeper than that basin. Because the more researchers looked at the differences between the near side and the far side, the more they realized that something fundamental must have happened early in the moon's history that set these two hemispheres on completely different paths. Remember those dark lava plains on the near side, the Maria? The reason they exist is because lava erupted through the crust and flooded low-lying areas. For that to happen, you need a few things. You need heat in the interior of the moon, obviously. You need that heat to be concentrated enough to melt rock, and you need the crust to be thin enough that the molten material can actually push through and reach the surface. The far side has a much thicker crust than the near side. This is a measured, confirmed fact. The lunar crust on the far side averages somewhere between 10 and 20 kilometers thicker than the near side in many regions. When lava was trying to push up through the moon's interior billions of years ago, the far side crust was simply too thick for most of it to break through. The lava cooled and solidified underground before it could reach the surface. That's why the far side is all highlands and craters instead of dark, flat plains. But then the question becomes, why is the crust thicker on the far side in the first place? And this is where things get interesting and a little bit mind-bending. One of the leading theories involves what happened right after the moon formed. And to understand this, you need to know a bit about how scientists think the moon came to exist. The most widely accepted theory of lunar formation is called the giant impact hypothesis. The idea goes something like this. About 4.5 billion years ago, shortly after the Earth had formed, a Mars-sized body collided with our young planet. This object, which scientists have given the name Theia, smashed into the Earth at an angle, and the debris from that collision, a combination of material from Theia and from the Earth's outer layers, was blasted out into space. Over time, that debris cloud orbited the Earth and gradually came together under its own gravity, accumulating into a new object. That object was the moon. In the immediate aftermath of this formation, the moon was almost unimaginably hot. The energy released by all that material slamming together would have been enormous. Scientists believe the moon may have had a global magma ocean covering its entire surface, a planet-wide layer of molten rock thousands of kilometers deep. As this magma ocean cooled over millions of years, different minerals crystallized out at different temperatures and floated or sank depending on their density. The lighter minerals floated to the top and formed the early crust. Now here's where the Earth becomes important in a surprising way. The Earth itself was also extremely hot at this time, possibly also covered in a magma ocean of its own, and all of that heat radiates outward. The near side of the moon, the side facing the Earth, was being constantly bathed in this radiation from our hot young planet. The far side, facing out into cold space, was losing heat more rapidly. The result, according to some models, is that the near side of the moon stayed hotter for longer. And a hotter magma ocean produces different minerals when it crystallizes. Particularly, it produces more of the heat-producing radioactive elements that we find concentrated in the near side's crust today. This would explain the thicker crust on the far side. It cooled faster, so it solidified more extensively. And it would explain why the near side has all those lava plains, because the near side's crust, with all those heat-producing elements baked into it, stayed geologically active longer. It was hotter, more prone to volcanic eruption, more likely to produce the kind of lava flooding that created the Maria. The moon's two faces were shaped by their relationship to the Earth from the very beginning of their existence. The near side was warmed by proximity to our planet. The far side was chilled by exposure to the void. And those early differences compounded over billions of years into the radically different landscapes we see today. But even that theory doesn't fully explain everything, because there's another idea out there that goes even further, one that requires a second moon. Yes, a second moon. Some scientists have proposed that early in the solar system's history, the Earth might have had not one but two moons, the larger one we see today and a smaller companion, possibly about 1/3 the diameter of the current moon. Both of these objects would have formed from the debris of the Theia impact. For tens of millions of years, they orbited the Earth together, a two-moon system, both gradually moving outward from the planet as the tidal forces between them and the Earth pushed them away. But this arrangement couldn't last forever. The gravitational dynamics of a two-moon system are complicated and ultimately unstable, and the theory proposes that after tens of millions of years, the smaller moon and the larger moon slowly, gently, at low speed in astronomical terms, collided with each other. Low speed in astronomical terms is still pretty significant. The smaller moon would have smashed into the far side of the larger moon at a few thousand kilometers per hour. Not fast enough to blow either object apart, but fast enough to dramatically reshape one of them. The result would have been the smaller moon essentially being smashed flat against the far side of the larger moon, adding a thick extra layer of crust to that hemisphere and burying whatever terrain was underneath. This would explain the thick far side crust in a completely different way than the heat radiation theory. Not because the far side cooled differently, but because it literally has more material piled on top of it, the remnants of a second moon that no longer exists as a separate object. Both theories are fascinating. Both have supporting evidence. Neither is definitively proven. And the only way to really settle the question is to get down into that South Pole Aitken Basin and analyze what's there. Which brings us to the modern era. Because while NASA spent 50 years avoiding the far side, another space agency finally figured out how to get there. In January 2019, the China National Space Administration did something that had never been done in the 60-plus-year history of space exploration. They landed a spacecraft on the far side of the moon. The mission was called Chang'e 4, and to accomplish it, China had to solve the fundamental problem that had stopped everyone else from trying: the communication problem, the radio silence, the 2,000-mile wall of rock sitting between the far side and every antenna on Earth. Their solution was elegant. They launched a relay satellite first, a spacecraft called Queqiao, which means Magpie Bridge, named after a bridge in Chinese mythology. They put this satellite into a very specific type of orbit, called a halo orbit, around a gravitational point, called the second Earth-Moon Lagrange point. This is a location in space about 65,000 kilometers beyond the moon, where the gravitational pull of the Earth and the moon balance out in a way that allows an object to maintain a stable position relative to both of them. From this position, the Queqiao satellite has a line of sight to both the Earth and to the far side of the moon simultaneously. It sits out there in space like a telephone operator, receiving signals from the lander on the far side and bouncing them back to Earth, and receiving commands from Earth and forwarding them to the lander. A bridge between two worlds that couldn't previously talk to each other. Once Queqiao was in position and confirmed working, China launched the Chang'e 4 lander and its companion rover, Yutu-2, which translates to Jade Rabbit 2. And on January 3, 2019, the lander came down in the von Karman crater, a massive impact depression right in the middle of the South Pole Aitken Basin. Think about that for a moment. The very first landing on the far side of the moon happened inside the largest impact basin in the entire solar system. The first foothold humanity ever established on this mysterious, unexplored, avoided half of the moon was right in the heart of the feature that scientists most desperately wanted to study. The Yutu-2 rover began its work almost immediately. It's still operating today, by the way, making it the longest operating lunar rover in history. And what it has found has been as surprising as scientists hoped. The rover carried an instrument called a visible and near-infrared spectrometer, a device that can analyze the chemical composition of rocks and soil by looking at how they reflect and absorb different wavelengths of light. And when it pointed this instrument at the floor of the von Karman crater, it found something that scientists had been hoping to find for decades, but weren't entirely sure they would. It found minerals that are believed to originate from deep inside the moon. Specifically, it detected what appears to be olivine and pyroxene, minerals that are thought to come from the moon's mantle, the layer that sits beneath the crust. This is exactly what scientists had predicted they might find at the bottom of the South Pole Aitken Basin, given how deep and how old that impact is. The collision that formed the basin was so powerful that it may have punched all the way through the crust and pulled up material from the mantle below. If confirmed, this would be the first time in history that we've directly sampled or analyzed material from the lunar mantle. That's the kind of discovery that fundamentally changes what we know about how the moon formed and how its interior evolved. And it happened on the very first visit to the far side. But the geology is only one part of what makes the far side so uniquely valuable, because the far side of the moon has a superpower that the near side doesn't, and it's a superpower that no other place in the inner solar system possesses: radio silence. We've been talking about radio silence as a problem, as the reason the far side was avoided for 50 years. But scientists figured out a long time ago that this same property could make the far side one of the most precious scientific real estate locations in the solar system. Here's the thing. We live in a world saturated with radio waves. Every cell phone, every Wi-Fi router, every television broadcast, every radar installation, every GPS satellite, every communication tower. The Earth generates an absolutely staggering amount of radio frequency noise in every direction, at every moment of every day. From the perspective of a radio telescope, the Earth itself is almost blinding. It's like trying to observe the stars while standing inside a stadium with every floodlight aimed directly at you. This is a serious problem for radio astronomers because the universe is also full of radio waves. Natural radio waves, radio emissions from pulsars, from galaxies, from the early universe itself. Some of the most important discoveries in the history of astronomy came from studying these natural radio signals: the detection of pulsars, the mapping of hydrogen gas across the Milky Way, the discovery of the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire universe and tells us what conditions were like just a few 100,000 years after the universe began. All of that science was done despite the overwhelming radio interference from human civilization. Imagine what we could learn if we could get away from all of that noise. The far side of the moon is shielded from Earth's radio interference by 2,000 miles of rock. It is the quietest radio environment in the entire inner solar system. Nothing we could build anywhere on Earth or in orbit around Earth can replicate that kind of silence. A radio telescope built on the far side of the moon would be orders of magnitude more sensitive than any telescope we've ever operated. It could detect radio signals so faint that they're currently invisible to us, completely drowned out by the constant roar of human civilization. And here's the frequency range that scientists are most excited about: the very low-frequency radio range, sometimes called VLF radio. These are wavelengths between roughly 10 meters and 10 kilometers, and they carry some incredibly important information. They can tell us about the conditions in the universe during a period called the Cosmic Dark Ages, the era before the first stars had formed, when the universe was filled primarily with hydrogen gas and nothing was glowing yet. We have essentially no direct observational data about this period because the Earth's ionosphere, the upper layer of our atmosphere, blocks these very low-frequency radio waves from reaching the ground. Space-based telescopes can't easily study them either, because they're too close to Earth, and the interference is still too significant. But on the far side of the moon, below a horizon of rock that blocks all of Earth's radio noise, a VLF telescope could potentially look back to the very beginning of structure in the universe. It could observe the cosmic dark ages directly. It could see things that no instrument has ever been able to see. Scientists have been dreaming about this for decades. There have been proposals for far-side radio telescopes going back to the 1980s. Some of the most ambitious concepts involve deploying antennas across the inside of craters, using the natural bowl shape of the crater as a reflector to create a radio telescope potentially kilometers across. NASA has funded early-stage design work on a concept called the Lunar Crater Radio Telescope, which would use robots to string wire mesh across the interior of a large crater, creating a dish that dwarfs anything we've built on Earth. These aren't science fiction proposals. They're real engineering studies. The technology to build them is coming within reach, and the science they could enable would transform our understanding of the universe's earliest history. But before we can build radio telescopes on the far side of the moon, we need to understand the far side much better. We need to know where the best sites are, what the terrain is like, what resources might be available, which is exactly what China's ongoing Chang'e program and NASA's own renewed lunar ambitions are beginning to address. The Artemis program, NASA's initiative to return humans to the moon, is specifically targeting the lunar South Pole as its primary landing zone. And the South Pole is interesting partly because of its proximity to the South Pole Aitken Basin and to the far side terrain. Some of the Artemis science objectives include studying the basin from a closer vantage point and preparing the groundwork for eventual far-side surface operations. But there's another reason the South Pole has become the most desired real estate on the Moon. And it has nothing to do with radio telescopes or geological mysteries. It has to do with water, ice. Specifically, water ice that has been sitting in permanently shadowed craters near the lunar poles for potentially billions of years. The lunar poles receive sunlight at very shallow angles, similar to how sunlight hits the polar regions of Earth during certain seasons. This means that the interiors of craters near the poles, the parts shielded from direct sunlight by the crater walls, have never seen sunlight. Not for billions of years. They are some of the coldest places in the solar system, reaching temperatures as low as -240 degrees Celsius. Cold enough that any water ice that found its way there would be frozen solid and would stay frozen essentially forever. And water ice has found its way there. Over billions of years, comets and asteroids have been hitting the Moon, delivering water in the process. Some of that water, when it landed near the poles and ended up in a permanently shadowed crater, simply stayed, frozen, preserved. This ice is enormously valuable for future lunar exploration, not just as a resource for drinking water or for generating oxygen for breathing, though those things are important. The most valuable use of this ice is as rocket propellant. Water can be split into hydrogen and oxygen, both of which can be used as rocket fuel. If you can make rocket fuel on the Moon using local resources, you dramatically reduce the cost and complexity of space missions. You don't have to launch all your propellant from Earth. You can fill up on the Moon. It becomes a refueling station for deeper solar system exploration. This is why everyone is suddenly so interested in the lunar South Pole. This is why there's essentially a new space race happening right now between multiple countries, all targeting that same region. The Moon went from being a visited and mostly forgotten destination to being the most strategically important location in the solar system within a matter of years. And the far side, sitting right there adjacent to all of this activity, is finally getting the attention it deserves. Let's go back to that South Pole Aitken Basin for a moment, because there's more to this place than we've talked about. Because even beyond its scientific importance, this basin has some genuinely strange characteristics that nobody fully understands. The floor of the South Pole Aitken Basin is anomalously dense. When spacecraft orbit above this region, and scientists measure the gravitational variations below, they find that the basin floor has a higher gravitational pull than you'd expect. There's something unusually dense sitting underneath it. One possibility is that the impactor that created the basin, the object that slammed into the Moon billions of years ago and carved out this 2,500-kilometer depression, might still be there, partially embedded in the Moon's interior. The collision may have been at just the right angle and speed to bury a significant chunk of the impactor deep in the crust, rather than completely destroying it on impact. If that's true, there's an ancient asteroid sitting underneath the Moon's south polar region, a visitor from the early solar system, perfectly preserved in the lunar interior for 4 billion years. Analyzing it would tell us things about the composition of early solar system bodies that we currently can only speculate about. The anomaly is real. The dense material is real. What exactly it is remains one of the open questions that future missions will need to answer. But the strangeness of the far side doesn't end with geology and gravitational anomalies, because there's something else out there that has been puzzling researchers since we first started mapping the Moon in detail. Something that sits right at the intersection of what we know and what we can't quite explain. The Moon's magnetic field is strange, or more accurately, the Moon's lack of a global magnetic field is strange in combination with the fact that some of its rocks are highly magnetized. The Earth has a strong global magnetic field, generated by the movement of liquid iron in our planet's outer core. This field extends far out into space and protects us from the solar wind, the constant stream of charged particles flowing out from the sun. Without it, the solar wind would gradually strip away our atmosphere. The Moon, by contrast, has no significant global magnetic field today. It's essentially magnetically inert. But here's the puzzling part. The rocks, lunar rocks, particularly those from the ancient crust, show signs of having been magnetized at some point in the past. They contain minerals that align with a magnetic field that must have existed when those rocks cooled and solidified, which means the moon once had a global magnetic field, and then it didn't. This suggests the moon once had an active liquid iron core generating a magnetic field, just like the Earth's. But at some point, that core activity stopped. The magnetic field collapsed, and we're not sure exactly when or why. What's particularly interesting about this is the distribution of magnetized regions on the moon's surface. The strongest magnetic anomalies are disproportionately concentrated in certain locations, and some of the most significant ones are on the far side, directly opposite the large impact basins on the near side. This is a pattern that is really difficult to explain and is one of the more active areas of debate in lunar science right now. One hypothesis involves the massive impacts themselves. When a giant asteroid hits a planet or moon, it can generate an enormous shockwave that travels through the entire body. That shockwave, meeting and focusing on the exact opposite side of the object, can create intense heating and geological disruption at the antipodal point, the location directly opposite the impact. Some researchers think this antipodal focusing of impact energy, combined with the moon's ancient magnetic field, could have created unusually strong magnetic anomalies at those locations. If correct, this would mean that the magnetic map of the moon's far side is essentially a record of the moon's ancient bombardment history, encoded in the rocks by a magnetic field that no longer exists. Every magnetic anomaly is a ghost of a collision that happened billions of years ago. We are reading the moon's past in its present magnetic signature, and most of that record is written on the far side. Now, there's something else about the far side that is going to become increasingly important as humanity begins returning to the moon in a serious way, and it's something that most people haven't thought about at all. The far side is the perfect place to hide from the sun. Not hide in a fearful sense, hide in a scientific and engineering sense. The sun is incredibly active. It regularly throws out massive bursts of radiation and charged particles in events called solar flares and coronal mass ejections. These events can be dangerous to unshielded humans and electronics in space. On the near side of the moon, there's no protection from these events. Any lunar base on the near side has to deal with 2 weeks of continuous sunlight followed by 2 weeks of darkness, and during those periods of sunlight, full exposure to whatever the sun decides to throw at it. On the far side, you have the moon itself as a shield. During the lunar day, when the far side sky is facing away from the Earth and toward the sun, yes, you're exposed to sunlight just like anywhere else. But during the far side's night, when you're on the side of the moon facing away from both the Earth and the sun, you have 2,000 miles of rock between you and essentially all sources of solar radiation. You are in the most shielded location in the inner solar system. This matters for very sensitive scientific instruments. It matters for certain types of manufacturing that require ultra-clean environments. And it will matter eventually for long-duration human habitation where cumulative radiation exposure is a serious health concern. The far side isn't just scientifically interesting, it's strategically valuable in ways that become more obvious the more you think about future lunar operations. But let's come back to what's happening right now, because the pace of exploration is accelerating in a way that would have seemed impossible just 10 years ago. China's Chang'e program has been systematically building toward far-side exploration for years. Chang'e 4 landed in 2019. Chang'e 5 successfully returned samples from the near side in 2020. Chang'e 6 was designed to do something even more ambitious, return samples from the far side itself. This is an extraordinary challenge. Getting a spacecraft to land on the far side is hard enough. Collecting rock and soil samples, loading them into a return vehicle, launching that vehicle off the lunar surface, and then getting it back to Earth, all while maintaining communication through a relay satellite, is an enormously complex sequence of operations where every single step has to work perfectly. China's Chang'e 6 mission launched in 2024 and targeted, once again, the South Pole Aitken Basin. It landed in the Apollo crater, collected samples from the far side surface, and returned them to Earth. For the first time in history, Humanity has physical pieces of the lunar far side sitting in laboratories where scientists can analyze them directly. The initial analysis of these samples is underway, and the results are already challenging assumptions. The material collected from the far side is different in composition from the near-side samples returned by Apollo and the more recent Chang'e 5 mission. The differences in volcanic material and ancient crustal rock are exactly the kinds of things that scientists need to start untangling the mystery of why the two hemispheres developed so differently. We are at the very beginning of understanding what those samples will tell us. It will take years of detailed analysis, but the fact that they exist at all, that there are far-side moon rocks on Earth right now being studied in laboratories, represents a genuinely historic moment in planetary science. And China isn't stopping there. Chang'e 7 and Chang'e 8 are planned missions that will continue exploring the South Polar region, including the far-side terrain. There are proposals for robotic missions that would explore the interior of permanently shadowed craters near the pole, searching for that ice we talked about. And there are longer-term ambitions for a permanent research station on the moon, partly positioned to take advantage of far-side access. Meanwhile, NASA's Artemis program is pressing forward with its own South Polar ambitions. The Commercial Lunar Payload Services program has been funding multiple commercial landers to deliver scientific instruments to the lunar surface. Some of those missions are targeting the South Polar region, and the scientific payloads being selected increasingly reflect the priorities that the far side represents: studying the subsurface, mapping the geology of the ancient highland terrain, measuring the magnetic anomalies, characterizing the radiation environment. There's also renewed interest in the far-side radio telescope concept. NASA's Innovative Advanced Concepts program, which funds early-stage research into ambitious ideas, has given funding to multiple far-side radio telescope concepts. One of the most ambitious involves using a robotic swarm of simple antenna elements deployed across the far-side terrain, all working together as a coordinated array to create an effectively enormous receiver. The individual antennas would be simple and cheap, but coordinated together and processed correctly, they would function like a single giant telescope. This is the kind of engineering that seemed purely conceptual a decade ago. Now there are serious proposals, funded research, and realistic timelines being discussed. The Far-Side Radio Telescope isn't a fantasy anymore. It's a near-future project waiting for the infrastructure to support it. And that infrastructure is coming faster than anyone expected, because there's a kind of positive feedback loop at work here. The more missions go to the lunar South Polar region, the more we learn about the terrain and resources there. The more we learn about the resources, particularly the ice, the more feasible it becomes to establish a sustained human presence. And a sustained human presence makes it possible to build far more sophisticated scientific installations than any purely robotic mission could manage. The trajectory is clear. The far side of the moon is the next frontier, and the frontier is opening right now. It's worth pausing to appreciate just how strange this moment is from a historical perspective. For most of human history, the far side of the moon was purely a subject of imagination. Writers and philosophers speculated about what might be there. Science fiction was full of far side scenarios because the mystery of it was irresistible. It was the great unknown, right there overhead, visible in the sense that you could see the moon, but completely opaque in terms of what was actually on that other half. Then we started exploring space, and for the first few decades, even with the technology to reach the moon, we still couldn't really explore the far side. We could photograph it from orbit, we could map it with radar, we could study it remotely, but actually getting down there, landing something, operating on the surface, that remained out of reach because the communication problem had no solution. And now, in the last 5 years, that has changed. The relay satellite concept that China implemented with Queqiao is straightforward enough that it's almost surprising nobody did it earlier. In retrospect, it seems obvious. Put a satellite at the right gravitational balance point, use it as a relay, problem solved. But that's often how engineering breakthroughs work. They seem obvious in retrospect. The hard part isn't the concept, it's deciding to actually do it, committing the resources, solving all the secondary engineering problems that come with implementation, and having the courage to attempt something that has never been tried before. China made that attempt, and it worked. And now the door to the far side is open. What comes through that door in the next 10, 20, 30 years is going to reshape our understanding of the moon in ways we can't fully predict. Because that's what happens when you finally go to a place you've been studying from a distance for half a century. The reality turns out to be richer and stranger and more surprising than even the best theories predicted. We went to Mars with robots and discovered that it had rivers and lakes and possibly oceans billions of years ago. We sent probes to Pluto and found mountains of water ice and nitrogen glaciers on a world we thought was probably just a featureless frozen ball. We flew past Jupiter's moon Europa and found compelling evidence for a global subsurface ocean of liquid water beneath the ice. Every time we actually go somewhere and look carefully, the universe surprises us. The far side of the moon is not going to be any different. We have theories, we have models, we have data from orbital observations and from the first surface missions. But when the real exploration begins in earnest, when humans eventually walk on that ancient rugged terrain and pick up rocks that no one has ever touched, and look back over the horizon at an Earth that is completely invisible to them, hidden behind the moon they're standing on, we are going to find things we didn't expect. The South Pole Aitken Basin will almost certainly reveal secrets about the moon's interior that overturn current models. The ice deposits at the pole might contain chemical records of the early solar system, preserved in cometary material that hasn't been altered in billions of years. The magnetically anomalous regions might encode information about the moon's geological history that we're currently only scratching the surface of, and a radio telescope operating in the far side's radio silence might detect signals from the cosmic dark ages that force us to revise our entire picture of how the universe's first structures formed. All of this is coming, not in some distant theoretical future, in the next few decades, in the lifetimes of most of the people watching this right now. The moon spent billions of years presenting only one face to us. We spent thousands of years staring at it, studying it, telling stories about it, and never knowing what was on the other side. We spent 50 years of the space age carefully, frustratingly, understandably avoiding it. And now we are finally going, finally looking, finally beginning to read the other half of the story that our nearest neighbor has been keeping to itself all this time. And we have only just turned the first page. The moon is not a solved problem. It is not a visited and understood world that we checked off our list back in 1969. It is a place of profound, ongoing mystery, and the half of it that we spent 50 years avoiding holds some of the most compelling scientific questions in all of planetary science: the origin of worlds, the history of the solar system, the resources that might fuel humanity's expansion beyond Earth, the radio silence that could let us hear the first whispers of the universe itself. All of it is out there, 2,000 miles of rock away from the side we know, waiting, as it has always been waiting, on the far side.